Okay, so we talked about reductions on Monday. Today we're going to, we've got one or two more things on reductions to talk about, but we'll spend most of our time talking about oxidations, talking about these reactions over here. Oxidation of alcohols is a major topic. We'll finish that off on Friday. In fact, we'll spend most, if not all the time on Friday on chapter 12. It's a much longer chapter than chapter 13. So these are the reductions of alkynes that we finished up with on Monday in class. The three different ways we can reduce alkynes. There's two other kinds of compounds. So we talked about reducing alkenes and then alkynes on Monday. There's two other types of compounds that we can reduce, and those are alkyl halides and epoxides. So remember that we've defined reduction as the replacement of a carbon heteroatom bond with a carbon hydrogen bond. And so a carbon halogen bond is a type of carbon heteroatom bond. And so if we replace that with a hydrogen, that's a reduction. And we would use lithium aluminum hydride, which is one of our metal hydride reducing agents, to perform that reduction. On Monday, we talked about our other two types of reducing agents, hydrogen gas. We talked about sodium and ammonia, delivering protons and electrons separately. And then this is our third class of reducing agent, the metal hydride reagents. And then we can also reduce epoxides with metal hydride reagents as well, breaking one of the carbon-oxygen bonds of our epoxide and replacing it with a carbon-hydrogen bond. In the first case, the water is actually not participating in the reduction. The water is in there to quench the flammable byproduct that results from the lithium aluminum hydride. And when we show you the mechanism, I'll tell you what we mean by that. So the hydrogen atom here is coming from the lithium aluminum hydride, not the water. But in the epoxide reduction, we have two hydrogen atoms. One is coming from lithium aluminum hydride, and the other is coming from the water. Okay? So let's look at the mechanism of this reaction. So, and it's the same mechanism whether it's an alkyl halide or an epoxide. It's just an SN2 reaction that is a reduction. So we drew the Lewis structure for lithium aluminum hydride and its cousin sodium borohydride on Monday. And remember that this is just a quirk of the way we draw Lewis structures. We draw the negative charge on the aluminum, but we know that since the hydrogens are more electronegative than aluminum, the negative charge is shared by those hydrogens. And so we have four hydrogens with each with a partial negative charge. So these hydrogens act similar to hydride or H minus. So what we do is we just use the aluminum hydrogen sigma bond, or one of the four aluminum hydrogen sigma bonds, as a strong nucleophile to attack this alkyl halide in an SN2 process. Okay, so we're just going to displace that halide. In this case, that's going to convert this methylene, or that CH2, into a methyl group. We're going to get a salt with our lithium cation and our halide leaving group, or anion. And then we're going to form alane, or AlH3, as a byproduct. This is the thing that's flammable, and so you want to make sure you destroy that with water at the end of the reaction. The lithium aluminum hydride is also flammable. I mentioned on Monday that we had a hydrogen fire in my lab this summer. Previous to that, we had a fire. It's not a common occurrence. I've been here at BYU for more than 18 years now and just had a couple of fires in the lab. But the other fire involved lithium aluminum hydride. So some of these reducing agents are quite flammable, and you have to be very careful with them. Okay, so So this is the mechanism for the reduction of alkyl halides. And since it's just an SN2 reaction, we know that the less substituted alkyl halides will react faster. Primary alkyl halides will react faster than secondary alkyl halides. So since our lithium aluminum hydride is a strong nucleophile, the hydride part of it is a strong nucleophile, when we're opening an epoxide, would we expect the hydride to attack the more substituted carbon or the less substituted carbon? The less substituted carbon. The less substituted carbon is attacked by strong nucleophiles. So we see here an example of that. This is the carbon that gets attacked by the hydride, and then we protonate the oxygen in the second part, generating the more substituted alcohol. And in this particular case, that less substituted carbon was not a stereocenter, but if it was, what would happen to the stereochemistry? It would be inverted, exactly. Okay, very good. Any questions about reducing epoxides or alkyl halides? All right, so now we'll start talking about oxidation for the remainder of the chapter. And whereas we began the first half discussing reducing agents, we're going to start here talking about oxidizing agents. There's two types of oxidizing agents that we will learn. The first is reagents containing an oxygen-oxygen bond. Okay? Oxygen-oxygen bonds are very weak. They're very easy to break. Oxygens have lone pairs, and those lone pairs repel each other. So when you have two atoms with lone pairs bonded to each other, usually those bonds are not very strong. And that's definitely the case with an oxygen-oxygen bond. And so whenever we have a reagent with an oxygen-oxygen bond and it reacts, we're going to be cleaving that bond. Okay, we can count on that happening at some point in the mechanism. So examples of these reagents, we have oxygen itself, although we're not going to use oxygen as an oxidant until we get to chapter 15 because it reacts via radical mechanisms. We have ozone. We know that ozone protects us from the harmful effects of ultraviolet radiation. Ozone can also function as an oxidant, and we'll see how that can happen. We have peroxides. Hydrogen peroxide, we've seen that as an oxidant already in the hydroboration oxidation, although we did not learn the mechanism of that. If we replace one of the hydrogens of hydrogen peroxide with an alkyl group, we get an alkyl peroxide. And then we can also have a peroxy acid. A peroxy acid is simply a carboxylic acid with an extra oxygen atom. Okay, so these are some of our oxidants that contain oxygen-oxygen bonds. And then our second category of oxidizing agents are reagents that contain metal oxygen bonds. Okay? And the most common ones have chromium-6 or manganese-7. Manganese-7, that's one that you're probably familiar with from general chemistry. You've probably known that potassium permanganate is an oxidizing agent. We're actually not going to use potassium permanganate much in this class, but there are chromium reagents, chromium trioxide, sodium dichromate, potassium dichromate. These chromium-6 reagents all require acid in conjunction with them in order to perform oxidation reactions. We'll talk more about that on Friday. These are involved in the oxidation of alcohols. But then there's a special chromium reagent that doesn't require acid. It's known as pyridinium chlorochromate. It's this species right here. It's a pyridinium salt, and that's referred to as PCC. Okay, and we'll talk about how that differs from these other chromium reagents when we talk about alcohol oxidation, primarily on Friday. So the oxidation reactions we're going to learn are summarized on this slide. So we can oxidize alkenes, replacing the pi bond of alkenes with carbon-oxygen sigma bonds, epoxidation, dihydroxylation. We also can cleave the sigma bond of alkenes, the sigma and the pi bond, generating aldehydes or ketones. That's known as oxidative cleavage or ozonolysis. We can do that with alkynes as well. And then alcohols, as we'll learn at the end of the class today, depending on the type of alcohol, you can obtain either aldehydes, ketones, or carboxylic acids when we oxidize them. So we can replace pi bonds with carbon-oxygen bonds. We can replace carbon-hydrogen sigma bonds with carbon-oxygen bonds in these types of oxidations. So the first one we'll talk about is the epoxidation reaction. We've already learned how to make epoxides. We can take alkenes and convert them into halohydrants using bromine or chlorine and water. And then we deprotonate the oxygen with sodium hydride. And with the Williamson ether reaction, we make an epoxide. But actually, people who are making epoxides in the lab don't do that because there's a one-step method of converting alkenes into epoxides, and that's what we're going to learn now. That involves taking an alkene, reacting that alkene with a peroxy acid, a carboxylic acid with an extra oxygen, and that's going to give us an epoxide. We're going to transfer one of the oxygens from the peroxy acid to the alkene to make an epoxide. And then our byproduct is simply going to be a carboxylic acid. So there are a lot of different peroxy acids that can be used in this reaction. The most common one is an aromatic compound with a benzene ring. This is called metachloroperoxybenzoic acid. And whenever we have long names like that, we tend to abbreviate them. So we just refer to this compound as MCPBA. So if you're wanting to use this as a reagent, you would just write MCPBA, and that would accomplish an epoxidation of an alkene. Question? It has to be a peroxy acid. So it doesn't just have to be MCPBA. You could have peroxyacetic acid, for example. So any carboxylic acid, but it couldn't be hydrogen peroxide, for example, or this alkyl peroxide. Those won't work in this particular reaction. Okay. So the mechanism of making a peroxy acid. The good news about that mechanism is that it is a single step. It's a concerted process, no intermediates. So it's a short mechanism. That's also the bad news because there are lots of bonds that are being formed and broken in that single step. So we have more curved arrows in one step of the mechanism than we've seen so far in the class. So let's go ahead and draw that. To save space, I'm just going to use peroxyacetic acid because we mentioned it doesn't have to be MCPBA. So I'm going to draw out my peroxyacetic acid here. And then I'm going to draw my alkene right here. Okay. So I've told you that oxygen-oxygen bonds are weak. And we know that the pi electrons of alkenes usually function as nucleophiles. And so we're going to start out this mechanism by having our pi electrons attack the oxygen at the end of the chain here. And then we're going to cleave the oxygen-oxygen bond. But we're going to use those electrons in the oxygen-oxygen bond that's breaking to form a new carbon-oxygen pi bond. But of course, we cannot do that unless we break the existing carbon-oxygen pi bond because we cannot exceed the octet at the carbonyl carbon. So we use the pi electrons of our in our carbonyl of our starting material to deprotonate our peroxy acid, okay, forming a new OH bond. To do that, we have to break the existing OH bond. So what we do with those electrons is we make a new oxygen-carbon bond, okay? And all that happens at once. We have 4 pairs of electrons moving simultaneously, as evidenced by these 4 curved arrows that we've drawn. So let's draw the transition state, and we're going to have a record number of partial bonds in this transition state. Okay, it's kind of a distorted 5-membered ring. Didn't do a great job of drawing that, but okay. So here's what our transition state looks like. Those 4 pairs of electrons that are moving result in 4 bonds that are being broken, 4 bonds that are being formed at the transition state. So we have 8 partial bonds here. And then when we get to the final product, here's our byproduct, acetic acid in this particular case. And then we'll draw our epoxide down here. Okay. Any questions about our one-step epoxidation mechanism? Yes, Noah. So you're saying, could it go to this one? In theory, it could, but you see we have a cyclic transition state here. That's a 5-membered cyclic transition state. If you were transferring it here, it would be a 3-membered cyclic transition state. So this one is more favorable. That's why we draw the mechanism in this fashion. Okay. So much like our reduction reactions, some of our reduction reactions can be classified as additions. Many of our oxidation reactions can also be classified as additions because we're replacing a pi bond with sigma bonds, which is what we're doing in this case. So whenever we have an addition reaction, we have to think about the stereochemistry. So what kind of stereochemistry do we have here? Syn addition or anti-addition? It's a syn addition. Why? Yeah, both carbon-oxygen bonds are formed to the same side of that alkene. In this particular case, this is unique among addition reactions because we're adding the same atom to both carbons in this addition. So it would be impossible to add a single atom to 2 sides of an alkene simultaneously. That would be geometrically impossible. So we have to have syn addition when we're performing epoxidations. So because of that, we have a situation such as is seen in this sample problem. We've seen similar sample problems back in chapter 10 with halogenations and halohydrin formations. This is a stereospecific reaction because specific alkene stereoisomers will give specific epoxide stereoisomers. In this case, the cis-2-butene is giving us a meso epoxide. We have a plane of symmetry here, so both of these are equivalent to each other. And then trans-2-butene is giving us a chiral epoxide, and it is forming that chiral epoxide as a racemic compound. And so stereospecific, one isomer of our alkene giving us one isomer of our epoxide, the other isomer of our alkene giving us a different isomer of our epoxide. Okay? So epoxidation is a widely used reaction. Epoxides exist in nature, as I mentioned to you previously back in chapter 9. They're also present in pharmaceuticals. They're also very useful intermediates because of the ring openings that they undergo. And so here's an example of an epoxide actually in nature. Disparler, this is one of those pheromones. This is the pheromone of the gypsy moth. So it makes, and it's a chiral molecule. And most chiral molecules, only one of the two enantiomers has the desired bioactivity. In this case, this is the enantiomer that excites the male gypsy moths. And this is the one that does nothing for the male gypsy moths. So we can make this. This is a cis epoxide. The alkyl groups are cis to each other. The hydrogens are cis to each other. So that tells us we would have to have a cis alkene in order to generate that cis epoxide. And on Monday, we learned how to make cis alkenes. We can perform a Lindlar hydrogenation of an alkyne. So this just comes from Lindlar hydrogenation of this alkyne. And since both of these alkyl groups are primary alkyl groups, then we can attach them to acetylene by just doing acetylide alkylations with these primary alkyl halides. So we can synthesize disparler using reactions, completely using reactions that we've learned in the class previously. Okay. Now there's some history related to disparler that involves BYU. There was an organic chemistry professor at BYU in the 80s and 90s. His name was Bryant Rossiter. Sadly, he passed away from cancer in about 1995 at a much too young of an age. But in 1981, Bryant Rossiter was a graduate student at Stanford working on his PhD thesis. And what he was trying to do was develop a chiral catalyst that would allow him to make one enantiomer of a chiral epoxide and not the other. We'll actually talk about that on Friday in class. And as a test case for his new catalyst that he was developing, he decided to make disparler. Okay, and he made only the natural enantiomer of disparler. And how did he know he made the natural enantiomer of disparler? Because he became a magnet for gypsy moths. Like most pheromones, it's very, very sensitive. And so gypsy moths were attracted to him for months after he made this compound. It was very difficult for him to get it all off of his skin. And in the story that I heard, so I didn't really know Bryant Rossiter, but I actually knew his PhD advisor who told me this story. He said that when Bryant was finishing up his PhD, he was interviewing for jobs. He was interviewing at pharmaceutical companies on the East Coast, and apparently there are more gypsy moths in the Northeast than there are on the West Coast, which he learned to his dismay when he went out there for his interview. He had all these gypsy moths around him. So he's probably, in hindsight, he's probably wishing he made the unnatural enantiomer, the one that doesn't excite the male gypsy moths, but then the story wouldn't be nearly as interesting. So we'll learn more about that on Friday, how to make one enantiomer and not make the other. Any questions about epoxidations? Okay, so another way to replace a pi bond of an alkene with carbon-oxygen bonds is to add two different oxygens and not just one. So this is referred to as dihydroxylation. Dihydroxylation, because we're adding two hydroxyl groups to our alkene. And we can do this in two ways. We can perform an anti-addition. So if these groups on our alkene were different, then we would get different products depending on the type of addition. And the one that I'm drawing for you here would be the product of anti-addition of those OH groups. Or we could perform a syn addition, where we would add both of the OH groups from the same side of the alkene. So again, if the groups on the carbons that were part of the alkene are different from each other, then these would be different diastereomers. Okay, and so sometimes we might want the product of syn addition, other times we might want the product of anti-addition. So it's important for us to have a method of doing both of these transformations. So we'll talk about the anti-dihydroxylation first. It cannot be accomplished in a single step, but it involves two steps that we've learned previously. So two reactions that we are already familiar with. So first, we would take our alkene. We're going to use cyclohexene in this particular case. And we're going to make an epoxide from cyclohexene. We're going to react it with MCPBA. Sorry. Okay. And then we are going to react the epoxide with hydroxide. We know that hydroxide is a strong nucleophile that will open our epoxide. And then we have to add water in the second step to protonate. And that's going to give us our diol product. Now, is this epoxide chiral? Sorry, I paused in the middle of drawing a curved arrow to ask you a question. It's not chiral. It's a meso compound. It has a plane of symmetry. So that means that our nucleophile could attack either of the two carbons of our epoxide, and the rates would be identical. So half the time we'll attack on the left, half the time we'll attack on the right. And so we're going to get two products from this reaction. Okay, this would be from attacking on the right. And then this one would be from attacking or opening that epoxide from the left. The rates would be equivalent to each other, so we get a 1-to-1 mixture. Unlike the epoxide, which is a meso compound, this is a chiral compound. There's no plane of symmetry in this diol, and so these two compounds are enantiomers. So the way we accomplish an anti-dihydroxylation is two steps: epoxidation, which goes by syn addition, followed by ring opening with hydroxide. That goes by inversion. So the combination of a syn addition with an inversion gives us the net result in the end of anti-addition. Any questions? Okay, so let's talk about the syn dihydroxylation. And that involves a reagent called osmium tetroxide, OSO4. So this is one that has metal oxygen bonds in it. Osmium is a metal. Osmium tetroxide is quite expensive. It's also toxic. It can cause blindness. We use it in my lab frequently. Nobody in my lab wants to go blind. So we try to use catalytic amounts of this material. And in order to do so, we use a co-oxidant that oxidizes the byproduct that we get from this reaction back to osmium-8, osmium tetroxide, so we can use small quantities of this reagent. Saves us money and is less hazardous. So the syn dihydroxylation has a bit more complicated mechanism than our epoxidation reaction. And so we're only going to learn the first step of this mechanism, because the first step is going to help us understand the syn stereochemistry. And then we're not going to worry about the subsequent steps in the mechanism. Some of these oxidations have complicated mechanisms, and so we're only going to learn certain parts or certain sections of those mechanisms. So here's we're going to use our same alkene as an example, our cyclohexene. And we're going to use osmium tetroxide. We'll draw that right here. So if we were counting oxidation states, we would say this is osmium-8, because this osmium has 8 bonds to atoms that are more electronegative. So that's a super electrophilic osmium. And we know that our alkenes are nucleophilic. So our alkene is the nucleophile. Our oxidants is the electrophile, but rather than attack the osmium directly, our pi electrons are going to attack one of the oxygens, and then that's going to allow us to push electrons from one of the osmium-oxygen pi bonds onto the osmium itself. Okay, so this is how we reduce the osmium by attacking the oxygen and breaking the pi bond. Okay. But then we have another osmium-oxygen pi bond that we can use to make a second carbon-oxygen sigma bond. So that's going to give us a bicyclic species looking like this. And then we'll put a lone pair on our osmium. We still have these osmium-oxygen double bonds. Okay. So in addition to being oxidation, where we've created 2 new carbon-oxygen bonds, this is also an addition because we've added these oxygens, and it's an addition that forms a new ring. So we can refer to this step as a cycloaddition. Okay, it's a special type of addition called a cycloaddition. So now we're not going to draw the remainder of the mechanism, but what happens at this point is we add sodium bisulfite, NaHSO3, in water, and the combination of these 2 reagents is going to cleave these osmium-oxygen bonds, and it's going to protonate these oxygens, and so that's going to give us our diol product. Okay. Is this diol chiral? No, here we do have a plane of symmetry. This is a meso compound. So this is the isomer. This is the product that we get from this reaction. Okay. And then we're going to form an osmium-6 species. We're not going to draw it out, but we've reduced our osmium from osmium-8 to osmium-6. So if we want to use it again, we have to regenerate osmium tetroxide, and that's where we use this other oxidant, this co-oxidant, which is called NMO. And I'll draw the structure of NMO for you. It stands for N-methylmorpholinium oxide. Okay. So we just call it NMO instead of using the long name. Without going into mechanistic details, we just transfer the oxygen from the nitrogen. This oxygen gets transferred to the osmium, and we ultimately regenerate the osmium tetroxide. But the key part is this cycloaddition step. How does this cycloaddition step account for the syn stereochemistry? Any ideas, Riley? Yep. 2 oxygens being added from the same molecule in the same step, and so they're going to approach from the same side of the alkene, generating that 5-membered ring. Okay? Any questions on our syn versus anti-dihydroxylations? Okay, so our next oxidation reaction is different from the others we've talked about because we're going to be cleaving both the sigma bond, or both the pi bond and the sigma bond of our alkene. So this is referred to as oxidative cleavage because we're breaking our alkene into 2 pieces. If we cleave both the sigma and the pi bond, we're going to break the alkene into 2 pieces. We can also call this reaction ozonolysis because we're using ozone as the oxidant in this reaction. So we can get different types of products depending on the type of alkene that we're using in this reaction. So here's an example. I'm just showing you a tri-substituted alkene. And we're going to use ozone. As you'll find, we have a second step in this reaction. There's a couple different reagents we can use, but zinc and water is one of the combinations. And when we do this, we can obtain a ketone. The left half of the molecule turns into a ketone in this particular case. And then the right half of the molecule turns into an aldehyde. Okay? So we can obtain ketones and or aldehydes from an ozonolysis reaction. Depending on the type of alkene that we have, we can form 2 aldehydes, 2 ketones, or a ketone and an aldehyde. Okay? So let's look at the mechanism of ozonolysis. And like the dihydroxylation with osmium tetroxide, we're only going to learn the first step of this mechanism. As you'll see, some of the remaining steps involve some pretty crazy chemistry. So we're just going to skip them. But the first step is going to help us learn why this reaction happens. So ozone is a molecule we talked about way back in the first week of class. Okay. I don't know about you, but that first week of class seems like it was about a year ago. This has been an interesting semester. But we used ozone to show us how to draw resonance structures. And this is one of our resonance structures of ozone. We have a positively charged oxygen in ozone. We have our nucleophilic pi electrons in our alkene. Rather than have those pi electrons attack this oxygen directly, similar to what we saw with osmium tetroxide, we're going to see these pi electrons attack the oxygen that is pi bonded to the positively charged oxygen. And then we're going to push the pi electrons onto that positively charged oxygen. But that's not all we're going to do. We have this negatively charged oxygen with 3 lone pairs, and we're going to use one of those lone pairs to form a second carbon-oxygen bond. So that gives us a 5-membered ring containing 3 oxygens. Okay, not a very common sort of a species. This has a name. It's called a mole ozonide. And then the next part of the mechanism is pretty crazy. So we'll just draw a couple of arrows here indicating that there's going to be multiple steps involving some rearrangement. So we're going to break this ring open and give us two pieces. And then those two pieces are going to recombine in a different way. Well, now we've cleaved a carbon-carbon bond. We've inserted one of our oxygens in there. We call this an ozonide. Okay, so you can see why we're not going over the mechanism of that. Question? Yeah. Yeah, there is a mechanism. I've learned it once upon a time, but I've never used it, so I've forgotten it. So I'm not expecting you to know it. It's one of those cases where the knowledge of it is not going to help you a whole lot at this level of organic chemistry. So we'll just skip it. But the first one is important. But once we get to the ozonide, there's one more thing we have to do. We actually have to perform a reduction. So we would use zinc and water because we have to cleave the oxygen-oxygen bond. That's going to be a reduction process. Or we can use dimethyl sulfide. That also functions as a reductant through mechanisms we won't go over. Allows us to cleave this oxygen-oxygen bond. And then we obtain our two carbonyl compounds, aldehydes or ketones, depending on the type of alkene that we started with. Okay? So it's important to know the reagents we use, ozone in the first step, one of these two reagents in the second step, and it's important to know the mechanism. This is, again, a cycloaddition. So it would be a syn addition, but obviously you can't see that in the products because we've cleaved the sigma bond by the time we get to the products. Okay? So ozonolysis was used classically before the advent of spectroscopy as a way of structure determination. Because before we had spectroscopy, it was easier to determine the structures of aldehydes and ketones than it was to determine the structure of alkenes. So if you knew you had an alkene in your molecule, you could perform an ozonolysis, determine the structure of the aldehydes or ketones you produced, and then you could mentally glue those back together to get the alkene that you started with. And that's what this sample problem does. This is the sort of thing that's not done in the lab anymore, but you do tend to see it on standardized exams. So you do want to practice those kinds of problems. We can also perform an ozonolysis on a cyclic alkene. And instead of converting that alkene into two products, it's just going to open the ring. Okay? So here we would obtain a ketoaldehyde, right? So we count 1, 2, 3, 4, 5, 6. This carbon becomes the ketone. This carbon becomes the aldehyde. 1, 2, 3, 4, 5, 6. This is the product that we would obtain from ozonolysis of this cyclic alkene. We can also perform ozonolysis of alkynes. Here we have 3 carbon-carbon bonds to cleave, 2 pi bonds and 1 sigma bond. We replace all 3 of those bonds with carbon-oxygen bonds. So we end up generating carboxylic acids when we perform oxidative cleavage of alkynes. In this case, if it's an alkyne, the intermediates we get don't require the reduction, they just require water. Okay, so ozone and water will allow us to form carboxylic acids. In this case, we'll get acetic acid from the left-hand part of the molecule. We'll get propionic acid, which is incredibly stinky, from the right-hand part. So this is not a reaction we want to do in the lab. All right, any questions about oxidative cleavage or ozonolysis? Yes, Claire.
All of them have the same first step.
Yes. Yes, the first step will be the same. It'll diverge from there, but we're only learning the first step. So, all right, so let's just take a couple minutes to introduce alcohol oxidation, which we will discuss in more detail on Friday. And alcohol oxidation has outcomes that differ depending on the type of alcohol you're starting with, because we're replacing carbon-hydrogen bonds with carbon-oxygen bonds. So the outcomes depend on how many carbon-hydrogen bonds we have. So if we have a primary alcohol, we have 2 carbon-hydrogen bonds on the carbon that's bonded to the oxygen. And here's our shorthand notation for oxidation. So we could replace one of those carbon-hydrogen bonds with a carbon-oxygen bond. That would give us an aldehyde. Or we could replace both of those carbon-hydrogen bonds with carbon-oxygen bonds. And that would give us a carboxylic acid. And on Friday, we'll learn that you can get either the aldehyde or the carboxylic acid, depending on which oxidizing agent you choose. If you have a secondary alcohol, we have 1 carbon-hydrogen bond on that oxygen. And so we only have 1 oxidizing product we can get, and that is a ketone. Okay? What about a tertiary alcohol? Can we oxidize tertiary alcohols? No reaction. We have no carbon-hydrogen bond on this carbon, so tertiary alcohols are inert to oxidation. It's only primary or secondary alcohols. We'll stop there, and we'll learn the reagents and the mechanisms of alcohol oxidation on Friday. Please make sure to exchange papers and summaries with a classmate if you have not done so already.